So we're going to talk for a few minutes about a more complicated version of the confidence interval for a proportion that we developed in an earlier video. Previously, we developed this formula for calculating the confidence interval for a population P using p hat, and we learned about how to find values of z star and whatnot. The problem is that this formula works well when the sample size is very large, but for smaller sample sizes, it doesn't work that well, meaning we may think we're creating confidence intervals that capture the population P 95% of the time, but they may in fact only be capturing the population P 92% of the time or 93% of the time. So there's a more complicated formula that is going to take us some tricky algebra to get through. But remember that in the development of this formula, we started off by saying that 95% of the values of p hat will be between these two values. And we solved both of those for p hat. And we started off with 1.96, but we eventually just replaced that with z star. So we said that 95% of the p hats will be between p plus this expression and p minus this expression, z star radical p times 1 minus p over n. So now what we're going to do is we're going to solve this equation for p. And the first thing we're going to do is we're going to subtract p from both sides. So this side over here will say p hat minus p. And then we're going to square both sides to get rid of that square root sign. So now this is p hat minus p squared. This is now z squared. I'm going to drop off the star symbol and just say z squared. The plus or minus doesn't matter after we squared both sides, and the squaring on this side just gets rid of the square root sign. So this is an equation that has p in it, like right here p times 1, but it also has p squared in it, p times p, and this here is going to be a p times p. So this is a quadratic equation in the variable p, and so we're going to try to make it look like a quadratic equation, ax squared plus bx plus c, except with p as our quote-unquote variable. Okay, so squaring this side yields this, and moving the n under the z squared and multiplying this out gives us this. Distributive property gets us to here. And then I'm bringing everything over here to the left-hand side. So this z squared over n times p is now over here. This z squared over n times p squared is now here. And then notice we have a couple different terms with p squared in them. So we're going to combine those with a coefficient of 1 plus z squared over n. We've got a couple different terms that have p in it. So we'll combine those with a coefficient of negative quantity 2p hat plus z squared over n. And then we've got this over here, p hat squared. So this is a quadratic equation in p with this value of a and this value of b and this value of c. So we're going to plug those into the quadratic formula that we should be all familiar with, and that gives this nasty expression here. And this we have to simplify. This is going to take several steps. If you don't follow all of these steps, that's okay. The end result is what's important here. Okay, so first of all, a little bit of a gimmick here. The z squared over n, I'm going to write as 2z squared over 2n. And the same thing with this z squared over n, I'm going to write that as 2z squared over n. Okay, then the next step is then to factor this 2 out of both of those terms and factor this 2 out of both of those terms. So that makes that 2 there and that 2 there. Then on the next step, all I'm doing is this 2, since it's being squared, produces a 4 in front of that expression. And under the radical, we have a 4 here and a 4 here, so that 4 can be factored out, but since it's under a radical, that's going to be a 2 out in front of the radical. And the whole reason for doing all that is that this 2 in the denominator is going to cancel out with this 2 and this 2 in the numerator, getting us to this expression here. Now we're going to simplify a little bit what's underneath the radical. First, this quantity here that's being squared, we're going to multiply that out, which yields this. And then this quantity here, we're going to go ahead and distribute, which gives us this. And notice after doing that we got a p hat squared and a minus p hat squared that cancel out. So that simplifies a little bit for us. And then we're left with this. So rearranging a little bit, we have z squared over n times p hat, and we have z squared over n times negative p hat squared. So we're going to write that like this. And then z squared squared is z to the fourth, of course, and 2n squared is 4n squared. So that's just rewriting what's under the radical. And then the other thing is, notice that this term has a z squared, and this term also has a z squared, so that z squared can get factored out, and when it comes outside of the radical, that'll become a z in front of the radical. So there's no more z here because we factored it out. There's still z squared here after taking a z squared out of the z to the fourth. And then kind of the final step here is to realize that this quantity p hat minus p hat squared can be written as p hat times 1 minus p hat. And this final expression here is referred to as the Wilson score interval, or sometimes just the score interval. And notice it has elements that we saw in the previous simpler version for a confidence interval, namely p hat plus or minus z times radical p hat 1 minus p hat over n. So that part is the same. This little term here, this little term here, and this denominator expression are all what's new. And also notice that as n approaches infinity, this quantity here approaches 0, this quantity here approaches 0, and this denominator will just approach 1. And so therefore, as n approaches infinity, the Wilson interval approaches our simpler version of the formula right here. To compare these two, I've done several different problems with a p hat of 0.2, but different samples resulting in a p hat of 0.2. So 10 over 50 is a p hat of 0.2. Here's the confidence interval that the simpler formula gives us. Here's the confidence interval that the Wilson formula gives us. And I do that for each of these, and you'll notice that by the time we get up to a sample size of 50,000, the two confidence intervals are identical. So, as I said before, as n approaches infinity, this more complicated formula approaches this formula. And in fact, the simpler formula is all that's taught in most introductory classes. But many authors nowadays think that since we have technology in our hand, or we have code that we can write, that there's no reason to use the simpler formula. We could always just use the Wilson formula. So let me show you how this is done on the calculator. I'm going to do a little code on the calculator now. The regular confidence interval formula here is built into the calculator, but the Wilson formula is not. So we're going to write a little program for the calculator for those of you that have a TI-83 or TI-84. So I clicked on the program button and I'm arrowing over to the new menu. I'm going to create new. And it's got the alpha cursor here, so I get the letter equivalent of any button that I press, and I'm just going to spell out Wilson. So I'm basically creating a program called Wilson, and it's not really that many lines. See if you can stay with me. Here's what we're going to do. For the first line, press the program button, arrow over to IO, and item 8 is clear home. we're going to do clear home for the first line of our program. That will just clear the screen when our program is run. Now, the program button, IO, go down to item 3, which says display, and then we're going to lock our alpha key. So we're going to do second alpha, and then we need quotes, which is the plus sign, and we're going to type out Wilson score interval. The space is this character here that's attached to the 0. Wilson score, and another space, interval. And then we need a quote to end that, which is the plus sign, and then enter. Okay, then we're going to ask the user of our program to enter a value for x, which is the numerator of the fraction that's our sample proportion. So program IO prompt, which is item 2, prompt x, enter. Then we're going to ask the user for the sample size. So program IO prompt sample size n. So I'm going to do alpha and the letter n, which is attached to the log key. Enter. And then we're going to ask the user for a confidence level C. So prompt, program button, IO menu, item 2 is prompt, and then I'm going to do alpha C. So we're asking for a confidence level C. And so the first thing we're going to have our program do with this information is we're going to figure out our value of Z star. So on the next line of our program, we're going to do second vars inverse norm, and the area that we want is the area 1 minus what they entered for C divided by 2. So if they entered a C of 95%, 1 minus 95% will be 5%, and 5% divided by 2 will be 2.5%. So we want that, and we're going to leave the tail. This doesn't show up on all calculators, but we'll leave the tail as left, and we're going to paste that. And that's going to be stored, press the store button right here, that's going to be stored in variable Z. And then we're going to take the absolute value of that. So math button, number menu, very first item is absolute. Absolute value of alpha Z, close parentheses, store into Z. So that way our Z-score will be a positive number. And then we're going to take our proportion, which is x divided by n, so alpha n, and we're going to store that in variable p for our p hat. And then here is our ugly, gruesome calculation. I'm going to try to get all of these parentheses and whatnot correct. So, parentheses, P plus Z squared divided by parentheses 2n. I'm basically coding in the Wilson score formula right now. P parentheses P plus Z squared over parentheses 2n close parentheses plus, and then I'm going to do a little trick here for the plus or minus sign. We're going to do second parentheses for a brace, -1, comma, 1, and then second parentheses for end brace. This takes care, this takes place of the plus or minus sign, or I guess I should say the minus plus sign. That plus or minus sign gets multiplied times z, alpha z, and then we have this ugly radical. So parentheses p, and then parentheses 1 minus p, close parentheses, divided by n. So that's the simple version of the formula, p times 1 minus p over n. But then we have this other quantity, which is plus z squared over parentheses 4n squared. So now I'm going to close parentheses on that denominator of 4n squared. I'm going to close parentheses for ending the expression that's under the radical. And then I'm going to close parentheses one more time to close this parenthesis. And that whole quantity is divided by parentheses 1 plus z squared over n, and close parenthesis on the denominator. So this expression, if I hit enter right now, this expression would give me two values. One of them with the negative version, one of them with the positive version. I'm going to take those two values and store them into list 1. So I'm going to do second and the number 1. So those two answers, the lower end of our confidence interval and the upper end of our confidence interval, that's going to get stored into list 1. Now, to make the decimal numbers a little bit easier to understand, or a little bit easier to read, we're going to round off both of those endpoints. So what we're going to do is math number round. We're going to round the contents of list 1, second and the number 1. We're going to round the contents of list 1 to 4 decimal places, and then we're going to store that back into list 1. And then all we have to do for our confidence interval, by the way, you could round off to 5 decimal places if you wanted to, but now all we're going to do is we're going to display, so that's program IO, item 3 is display. We're going to display the contents of list 1. Okay, so that's the end of our program. I'm going to quit to get to the home screen, and I'm going to try to run our program called Wilson. So execute Wilson. So notice it gives us a blank screen and it says Wilson score interval. So using what we did over here on this document, so a p-hat of 10 over 50 with 95% confidence. So I'm going to say x is 10, n is 50, and c is 95%, which I'm entering as a decimal. And there's the Wilson score interval, 0.1124 right here, and 0.3304 right here. So we can do the Wilson score interval now. We have a program that we just wrote on our calculator to do the Wilson score interval. So that gives us this result here. If we're doing the simpler formula, that's already built into the calculator. Stat tests 1 proportion z interval, and we say 10 out of 50 and 95% confidence level, and this gives us 0891, which is here, and 3109, which is here. So that's how you use both formulas, or that's how you do both formulas on the calculator. The simpler one is built in, one proportion z interval. This one here, you have to do a really hideous calculation by hand or write a quick little program for your calculator. So that's what you need to know to work problems that require the Wilson score interval instead of the simpler formula.